The next topic here, phasors. What we see is the form of the equation here and the form of any kind of steady state response, just like we've seen before. We rewrote it in terms of exponentials, and the sources would have this form of the exponential, and it implies responses of this form of the exponential. Notice two different phase angles, theta for the source, phi for the response. There will be a phase difference between the response and the source functions. We rewrite the source function like this, and we get this here. We're defining new variables that little u is going to equal to um, and at this point I'm going to go ahead and get my marking. So we're saying little u here is going to equal to the part times the e to the j theta part. Little y is going to be equal to the, and they didn't do that for y. They didn't show, they showed they didn't show ym. That little y is going to be the ym part and the phi, the phase angle part. I think way early on, the only information you really need to know is the magnitude, the amplitude, and the phase angle. So instead of writing all this stuff, we have a shorthand notation. What I said earlier about the angle in degrees versus radians, be careful about that. You can get fooled. So theta is often expressed in degrees, but when we're actually doing mathematical equations, we're actually programming computers to do it and things, we need to remember omega t is a radian and convert from degrees to radians. This is the phasor representation. We just specify the magnitude and a phase angle of a signal. Everything's at the same frequency. Okay, it's a shortcut, so we can start working with things. So here's the same circuit we had before. We write it in its phasor form. So we have the response. We can just consider this stuff here. We don't have to consider everything in the world. Writing down the equation, and remember that we were able to factor this out, the e to the j omega t, and go around and solve everything. You have to work with complex numbers. That's the point of this. That's what that little statement says. And now, this is why we do it. You don't have to worry about differential equations so much. Okay, so a couple identities that remember that the sine of the angle, so this here, we have a cosine, and phasors use cosines, by the way. They use cosines. So the cosine of this is equal to the sine of this. That's the point. So we have a response function. We can write down the phasor. We can ignore the 377. Responses and sources are all going to be 377. So we don't write that down. We just write this down. And a couple other examples. F equals 400 hertz. I frankly don't care. Omega would be 800 pi. But we can start working problems using these two numbers. And similarly, we can just keep going with this idea. So you combine things with the rules of complex algebra. Magnitudes in complex algebra. Remember, this is V1 times e to the j theta, theta 1. And this is V2 e to the j theta 2. So we can write, you multiply the two amplitudes together. When you multiply two phasors together, you're multiplying the amplitudes. You're adding, this is in the exponent. Remember, this stuff is in the exponent. So you can add the angles. But it's, as you can see, it's starting to look pretty darn easy. Division, very similar. Okay, let's think about how to use phasors in this way. The phasor representation for I, in this case, let's go down here. V and I track with each other. They are at the same phase angle. So if you have a resistive circuit, there's no change. The phase angle for voltage is the same as the current. In a graph, if you graphed it, you're graphing the imaginary numbers on the vertical and the real part of a signal on the horizontal. So the real imaginary part of a complex number vertical, real part horizontal. And the current is exactly in line with the voltage if you have a purely resistive circuit, Ohm's law. The two are, quote, in phase. Okay. This graph expresses it. Inductors, a little bit different. So we're going to get a j omega come out when we differentiate the current, and that j is e to the I pi over 2, or e to the j. Anyway, the j, might as well write that down. J equals e to the I pi over 2. Sine of pi over 2 is 1, cosine of pi over 2 is 0. Equals e. And remember that people, and I'm flipping my j's and my i's. Got to be careful about that. In some applications, people use I omega t. And in electrical engineering, we want to use j omega t. We don't want to confuse the complex constant with current. Okay, e to the j, 90 degrees. So we can use that fact to build it in, to bring it in as a phase angle. Let's keep going with that then. There. That's exactly, as phasor notation, that's exactly what I just said, right here. And the book author converted it to phasor notation. Okay, so the relationship between voltage and current for an inductor, for this inductive circuit, is given by this. And this expresses the idea that the voltage is here. It leads the current. It's 90 degrees in advance of the current. And we look at, instead of a plot like this, plots angles and sinusoid waves and things like that. Remember on a circle that the sine is given by the height and the cosine is given by the length on an xy plane? Well, now instead of an xy plane, we're doing real and imaginary planes. Real and imaginary numbers, excuse me. Okay. So, we want to find I of t for this for L of 20 millihenries. And so we can write, the first thing we do, write down the phasor representation. So where did this come from? 12 at 20 degrees phase angle. Oh, there we go. There's V of t. And we know L, so we can use this expression here, this formula now, rearrange it to get this. So I equals, there, let's go there. You've got division, so it's 12 over omega L. We just take this becomes our lead, and 20 minus 90 becomes our new angle. There. Of course, you can crunch numbers. I didn't crunch the numbers, but there it is. Okay, let me stop here. We'll go on to capacitors next time.